Okay, let's start. So, morning everyone. Hope you had a good weekend. So, last week we talked about Dijkstra and how it builds on top of breadth first search to be able to do path search in like a relatively short time. And we saw that how just changing the data structure used in the algorithm while keeping everything else almost the same gave us a lot of CPU time. However, can we still do better? Dijkstra is still not smart enough, and we talked about it at the end of the last lecture. So we know with Dijkstra that we are expanding the wavefront in like circles around the source. So you notice here that we start with almost all the neighbors that are close to the source, and from there we expand to their neighbors and so on until we reach the destination. But we notice here that, sorry, let me grab this. Yeah, we notice here that all of this portion, almost always we probably won't need it because intuitively, if we look at this paper map, we know that the path will be somewhere around here. So we are kind of wasting CPU cycles by trying to visit these nodes and expanding from there as well. So we want to try to find like a better algorithm to do this. Okay, so yeah, why are we examining the nodes in the wrong direction here if we're not going to use them? So there are several approaches to do this. One of them is a very popular class of algorithms called A-star algorithms. So A-star algorithm is a collection of algorithms that build on top of Dijkstra, but they try to limit the search space, or they try to reorder how we visit the candidate nodes somehow based on some intuition from the user, from the developer. And from the knowledge we know about the underlying problem, which is in this case the graph of a city map. So we do this in order to be able to try to reach the destination faster and save some of the CPU time. Okay, so these are called domain-specific heuristics. A heuristic basically is just some technique that the developer applies based on their knowledge and based on some intuition behind the problem they are working on. Okay, so for example, we can, since we are working on the city map and we know from, we know the coordinates of each node, so we can estimate how far are we right now from the destination to be able to change the priority. I'm going to choose let's say I'm going to choose the nodes that are relatively closer to the destination from the ones that are further behind. But at the end of the last lecture, we saw like an example that if we cannot throw away nodes, all of what A-star is doing is trying to reorder the nodes. If we throw away nodes, it might be too harsh, and we might throw away nodes that are actually needed to be able to even find a path. So for example, in the last lecture, we talked about like trying to cross a highway like 401. We have to go out of our way in order to find some node that connects us to the other side of the highway. So if we just like constrain ourselves of all with the nodes that are within a certain distance from the destination, then we're probably being too harsh. What we are trying to do here is just reorder what we have in the priority queue, or whatever we use in whatever heap we use in Dijkstra, in order to try and gain some CPU cycles. Okay, so yeah, we talked about, like, we saw that how Dijkstra basically goes in circles outwards. What A-star tries to do is trying to go into these approximately ovals, okay, and trying to limit the search space towards the destination. So we are still visiting nodes here because sometimes we probably need to, again, to loop around nodes to get out of blockages like the highway, sorry. But almost always we are trying to go towards the destination directly. Okay, so mostly searches in the right direction, but we'll still explore some in the other directions so that we can guarantee that we are finding a legal solution. Okay, so yeah, as we said, the key to A-star is to sort the wavefront differently. We call these approaches heuristics. We want to guide the algorithm based on our knowledge of the graph so it can prioritize the nodes that are closer to destination. Okay, so So for example, let's look at this graph. So this graph is, let's say it's taken from our Toronto map. We have this source and we have this destination, and we've already started with Dijkstra and filled in the wavefront and pulled N1 and N2 out of the wavefront. So we know that the best time to reach N2 is 45 seconds, and the best time to reach N1 is 30 seconds. Okay, so we can also measure the distance, current distance from N2 to the destination. Let's say it's 1 kilometer, and that of N1, it's gonna be 1.5 kilometer. Okay, so if we are using Dijkstra right now, the next thing that we're gonna pull out of the heap is what? Is gonna be N2, N1, because it has a smaller travel time, right? So, yeah. Let's think together, basically how we can fix what is the priority in the priority queue so that we can change the order of the nodes somehow. Anyone has any idea? Yes?
I don't know if this is relevant, but like, would some sort of like penalty or deduction be applicable based off of?
Some sort of what, sorry?
Would some sort of like penalty or deduction be applicable if it's a further distance compared to another, like a node you're looking at?
Okay, so you are on the right track. Basically, we are trying to penalize the nodes that are further away from the destination. But how are you gonna do that?
A heuristic function, I assume.
Yeah, so right now, we store the nodes based on what? The travel time, right? Yeah. We probably have to combine the distance somehow with that travel time so that we change the cost function in the priority queue, right? Let's call it a cost function. So first of all, how are you gonna calculate that distance?
You probably have a function where like it changes like the weight of the path based off of some combination of your travel time and the distance from your current node.
Yes, but let's focus how we're gonna measure that distance. Like what distance are you taking here?
From the current node in the path you're taking and the destination node.
Okay, but we still don't know the path from the current node to the destination. So, like, remember in milestone 1, we calculated the distance between two intersections based on the crow flies distance, like just the direct distance. Let's assume that we are flying from the current to the destination, and this is the distance we're going to take. It's not accurate, probably. Most probably, it's not going to represent how we're driving along the path. It's just like an approximation how far we are from the destination. That's right. Okay, so we took the distance, and we have the travel time, but we need to weight them somehow so they are like equally proportional, like equally contributing to the cost function, right? Because these are different units. One is in kilometers and one is in seconds, right? So how can we modify, or how we can leverage that distance to be able to match it with the whatever travel time we have? Anyone has any idea? Nope. So again, we have a distance. The unit is in kilometers. We calculate it based on like the one of the functions in M1. We know that it's running quickly, so we can do a lot of distance calculations. And we have the travel time, which is the best time right now to arrive at the current node from the source, right? While visiting all of the graph, traversing the graph. So the problem is the distance has a unit of kilometers, the travel time has a unit of seconds. So we want to try and match these together to be able to use them as one cost function or one unit that we can prioritize nodes upon. You have an idea?
Okay. I don't know if it's relevant, but like, what if you took the distance to get to your current node and divide that over time to get the rough like speed it took to get from your source to that node, and then you could use that speed to know how long it might take to get to your destination?
Okay, so you are on the right track, but why are you trying to get dividing the distance from the source to the current node?
Because we know the time from the source to the current node, so I'm trying to take an average of the speed from the source to the current node.
But exactly, we know the time that's going to take for us to get from the source to the, so this is the best time. We cannot do any better than it, right? So let's keep it as is. We want this travel time, but what you said, we should apply to the other portion. We should basically take the distance from the current node to the destination, divided by some speed limit, okay? And then get a travel time, an approximate travel time from the current node to the destination. We're just predicting or like trying to find how long it's going to take us to go from here to the from the current node to the destination. Now, again, this is an approximation. This is not accurate. We currently don't have any path to find the actual travel time from, right? So, okay. So again, this is the right approach. We assume that a crow flies distance. Again, this is like just assuming that we are flying. There are no obstacles from here to the destination. This is the distance that we're gonna test our algorithm upon. We assume that we drive at a certain speed limit. Let's call this speed limit x. Okay, for that crow flies distance, and then we use that to predict the expected time to the destination. So let's assume that x is going to be the average speed limit in the city. Let's say that this is 60 kilometers per hour, okay? So if that's the case, then to get from N2 to the destination, it's going to take us 1 kilometer over 60 kilometers per hour. That's around 1 minute, right? 60 seconds. On top of the 45 seconds that we already know this is the best time to get to N2, that would tell us that to get from the source to the destination, through N2, it's going to take us overall 105 seconds. While for N1, it's 1.5 kilometers away from the destination. So we divide that by the 60 kilometers per hour, and that's around 90 seconds. On top of the 30 seconds, that's 120 seconds. So right now, what are we going to choose first? We're going to choose N2 because it has an overall travel time, or approximate travel time, that is less than N1, right? So with Dijkstra, we are choosing N1 first, while with this approach, we are choosing N2 first. Now, is this correct or not? We still don't know, right? But let's say that we took N2 to be our next node to test upon, okay? And say that after traversing from N2, we reach this node N3, which is 30 seconds away. So basically, our approximation of the speed limit was correct. Let's say that it was correct. It was 60 kilometers per hour. Okay? So we know now the best time to reach N3, based on all of the information we have in the graph, is going to be overall 75 seconds, 45 plus 30 seconds here. And we are still 0.5 kilometers away from the destination, while N1 is still 1.5 kilometers away from the destination. Okay, so now we apply our approach, our heuristic again. Again, all we are doing here is just changing the cost function in Dijkstra. We're not doing any more code on top of it. Okay, so for N3 right now, we have 75 seconds, which is the best time to reach to this node. On top of that, we have 30 more seconds, which is calculated based on our heuristic, which is the 0.5 kilometers away from the destination, divided by, again, our average speed limit, 60 kilometers per hour. Okay, so that will, again, give us 105 seconds. For N1, it is still 30 plus 90, it's 120 seconds. Okay, so again, we're going to choose, in this case, N3, right? Because it's still, the overall travel time is still less. So, okay, we visit N3, okay, we reach the destination, we find that the approximation of the travel time was correct, it's 60 kilometers per hour. Sorry, the speed limit was correct, it's 60 kilometers per hour. Our overall approximation was also correct, and we were able to reach the destination faster. So instead of visiting N1 from the beginning because of Dijkstra, we opted to choose another path and probably prioritize the nodes that are closer to the destination. So there's still one tiny problem here. In most cases, this will probably work, but let's look at this example. Let's say that if you've taken N1 already, you find out that actually the road to take from N1 to the destination is actually a highway, and the speed limit there is 100 kilometers per hour, right? So actually, the time to get from N1 to the destination is much shorter than what we predicted. Right? We predicted 90 seconds because we assumed that the speed limit is 60 kilometers per hour, but in this case it was actually faster, and it was actually 84 seconds. So we should have chosen N1 from the beginning instead of N2, right? Based on our approximation. So how can we fix this? Anyone has any ideas? Yes?
Should you like keep searching other nodes until you reach a point where that node matches or is greater to the current fastest time to the destination?
Choose other nodes until, can you repeat that please?
Like you know how you should have also put that node and not just stop when you found the first match?
Okay.
If you have other nodes to visit in your queue, then to also visit those until those paths end up being greater than the fastest time.
Okay. So remember when we talked about birth first search, what the problem with it, that we had to re-expand instead of just marking the nodes as visited? And that re-expansion, we couldn't put a time bound on it, right? Because we might have expanded the whole graph again. So in this case, we might actually run into the same problem. Like if you keep searching through the queue, after even reaching the destination, you will have to re-expand from the nodes that you find that you reach a better travel time from it, right? And that will give us the same problem that we had with the breadth first search, right? So we're trying to avoid that. We're trying to say that as long as you reach the destination from the first time, it's guaranteed that this is the best travel time that you're gonna have. Okay? Any other suggestions? Like how can we avoid over-predicting what is the travel time from the current node to the destination? It's not a trick question, by the way. It's like just a minor fix for the approach that we've taken so far. Okay, so to guarantee that we are getting the best path always, we should not over-predict. So what we are doing here is approximating what is the travel time that it's going to take us to go from the current node to the destination. But that should be either the equal to the optimal solution or less. We should not over-predict, otherwise we're gonna run into the problem where we actually didn't visit nodes that we should have visited because they are on a highway, right? And the way to do this is to always assume the maximum speed limit in the city, okay? Because let's assume that all of the roads that we're gonna take are going to be, let's say in Toronto, it's 100 kilometers per hour. This is the maximum speed limit. You usually find this in load map and hash it somewhere. So we will always assume that in our approximation to go from the current node to the destination, we're gonna take 100 kilometers per hour. So would that fix our problem? Let's see. If we're visiting, so right now we're back to the problem where we're comparing between N1 and N2. And remember, Dijkstra will just choose N1. Here we're trying to prioritize based on distance as well. So with 100 kilometers per hour, N1 will be 30 seconds, which is the best time, plus 1.5 kilometers over 100 kilometers per hour, that's around 54 seconds, so that's 84 seconds, right? N2 is going to be 45 seconds plus 1 kilometer over 100 kilometers per hour, which is around 36 seconds, so that's around 81 seconds. So we're still choosing N2 here, right? But let's take it. So we take N2, and then we check N3, which is from the previous slide here, N3 with N1, right? So N3 is 0.5 kilometers away, and it has 75-second best travel time right now. Because again, we find out that the actual speed limit is 60 kilometers and not 100 kilometers here on this portion, right? So we take that 75 plus 0.5 kilometers over 100 kilometers per hour, and that's around 18 seconds. That's gonna give us 93 seconds. Okay, so now we're choosing between N3 and N1. N1 has a better approximation in this case, 84 seconds. We're gonna take that. Okay, we take the N1 and we find out that this is a highway and we actually reach the destination through a faster route. Yeah, go ahead.
How is it over-predicting? Isn't that like under-predicting the best time? Like because with our previous speed limit, we predicted a time that was worse. So wouldn't that be like under-predicting the best option?
You're looking at it from the outside. Over-predicting in terms of we're gonna reach it faster, right?
Predicting the time.
Yes, yeah. Any questions on this? So right now, with the speed limit, with the maximum speed, if we assume the maximum speed limit in the city, in our heuristic, then it's guaranteed that we're gonna find the optimal path, and it's guaranteed that we're not gonna overpredict. There is a proof of this. We're not gonna go over it. It's outside the scope of the course, but in ECE297, I think, with the algorithms and the structures, you're gonna basically do a lot of proofs on these things and try to prove that this is actually gonna achieve the optimality. Okay, questions? Nope, okay. Okay, so let's talk about implementation. All what we've done so far on top of Dijkstra is just trying to change the metric that we sort our priority queue or our heap with. So we are just changing the way we are sorting the wavefront again. Not the best time found to the node. That, remember, we had two data structures. One is called wave element, which is whatever we populate in the heap, and another is called node, which is the global data structure that we store the best travel time to reach each node. So that should not be changed. That data structure is still global, and it's still the one that we're going to use to find the path or backtrace the path from. So that it should always store the best travel time to get from the source to each node in the graph, right? What we are changing is just the wave element data structure. So remember, we had the node ID, the edge ID that we used to reach that node, to reach that candidate node. The travel time, which is still the best travel time to reach that candidate node from the source. On top of that, we're gonna add another metric, is whatever your idea of a heuristic. In this case, what we just talked about is approximating based on the distance and the maximum speed limit. Okay, so when we're trying to traverse the graph, we're going to add these two elements in order to push to the queue. And the queue will sort itself based on the summation of these two elements. Is that clear? So A-star is like an important algorithm for you to pass the very hard test cases in the milestone 3. So if you have any questions, now it's your chance to ask. Okay, let's look at a quick demo for A-star here from the golden solution. Oops. Okay, so we showed Dijkstra last week. Let's look at it again. So I'm gonna choose a node here, and notice that how we're expanding in kind of circles outwards, right? So if you choose another one here, it's basically trying to traverse the whole graph. Now let's change to A-star. And okay, now notice that it's not a circle anymore. It's kind of more directed towards the destination. Why is that? Because we are using now this heuristic that reorders the nodes in the priority queue somehow to prioritize the nodes that are closer to the destination. So we're still finding probably the same path as Dijkstra will find, which is the optimal solution here, but in a less CPU time. Make sense? Okay, so that's it regarding the algorithm. Any questions on it? Yes?
So, like, for Dijkstra, when I look at A-star, is the general structure pretty much you look at, from your source node, you look at nodes that are surrounding it, and you add it to a priority queue based off of now not only the time to get to that node, but also the most ideal time from that node to the destination, and based off that sorts what node we look at next.
Yes, so that's A star, not Dijkstra. Dijkstra is still looking at the travel time, right?
Without A star, it would just look at what is the shortest node, like time to get from the source to a node.
Yes. So in A star, we're adding these two terms, the best travel time and the approximate travel time is going to take us from this current node to the destination, right? If you can think of it like as Dijkstra is still the same, but we are assuming that it's going to take us 0 seconds to get from the current node to the destination, and we just left with this node, with this first term.
Can you repeat that? What you mean?
So in A star, it's the best travel time to reach this current node, plus the approximate travel time from the current node to the destination, right?
Assuming a most ideal speed.
I'm assuming the maximum speed in the city. In Dijkstra, you can think of it as we're actually not assuming the maximum speed, we're assuming an infinite speed, so that it's going to take us 0 seconds to get from the current node to the destination, and we are only prioritizing based on how long it took us to reach here.
Yes, so it's looking at the priority queue is only focused on the time from the source to the node. And
Yes, so it's the most pessimistic approach because we don't have any other information other than whatever it took us to get here, right? That's why in A star we're basically adding an extra term so that we can push the algorithms or guide the algorithms towards the destination.
Instead of just like going out.
Yes.
Okay.
Yeah. Okay, so just to go over milestone 3, I hope that everyone started on milestone 3 already. I know I still have around almost a week, but yeah, don't leave it till the end. Like it's gonna be very hard to debug the last 2 days. Okay, so if you look at milestone 3 unit test, you see exercise 3, you're gonna find that it has a lot of tests, right? And it spans like around 3 cities. But these are divided into several categories to help you basically be able to debug the algorithm in a faster way. Like the problem with the challenging part of this milestone is that you're trying, the code that you're gonna write is not that much. Dijkstra shouldn't take you like more than 100 lines of code, but the thing is, it's very hard to debug. Why? Because you are trying to find paths between different intersections across the city that can span the whole city, and you're basically working with large data. In Tokyo, for example, you're working with over 1 million nodes, right? So it's gonna be very tough to debug if you don't have these small unit tests to make sure that you are doing the right thing or make sure that your code is robust. Okay, so the tests are divided into several categories as follows. The first one is called the path cost, and these are marked by func_path cost. These don't have any marks on them. They are just for you to make sure that you are measuring the travel time of any given path correctly. So we're gonna pass to you a random path in the city. We're gonna pass to you a turn penalty, and it's your job to just try to calculate the overall travel time of that path. Just go over each street segment, get the travel time, plus the turn penalties if there are any turns, and that's it. Okay, so that's again just for you to make sure that your calculation is correct. The second one is called simple legality, and in this case we are just testing that you are able to find any path, not necessarily the optimal path, between intersections that are very close to each other, that are like either 1 hop away or 2 hops away from each other. So this is just, again, to test, to make sure that your code is able to handle these small cases. Because if those small cases are not working, probably the overall algorithm will not work, right? So we're just gonna make sure that you're able to find any path between 2 intersections that are 1 hop away, right? Then there are the legality paths, which are similar to simple legality, but these are nodes that are further away from each other. So again, these don't necessarily test the optimality of the path. They just test that you are able to find a path, and even if they are even if the intersections are very far from each other. Okay, and then similar to the simple legality and legality, there are simple optimality and optimality. Now these ones test for optimality, but again, the simple ones are just between nodes that are 1 hop or 2 hop away from each other, so they are very close to each other. And optimality is like for any path in the city. Now for any 2 intersections in the city, are you able to find the optimal solution? Or if there is no path between them, are you able to return the right thing? Okay. So there, in some cases, there might be several solutions that achieve the same optimal travel time, and you are free to choose any one of them. What we are going to do is that take the path that you are returning, measure the overall travel time that's going to take, and see if it's within a certain threshold from our golden solution, right? If that's the case, because we know our golden solution is going to return the optimal path, so any optimal path that you return, even if it's not the same actual path, it's fine. Finally, so all of these are, they will test the functionality of your code. And the last thing that we're going to grade you upon is the performance. So they are divided into medium, hard, and very hard CPU time. Now it's called very hard, it's not that very hard actually. So if you implement A star, you should be able to pass it. The way we do it, like we don't fine tune our golden solution. We just try to implement A star and multiply that by around 2.5 to give you the threshold that you have to meet, right? So if you implement Dijkstra, you should be able to pass most of these, or except the very hard test. With A star, you should be able to pass everyone. Like, assuming that your code is correct, you should be able to pass all the tests. Any questions on this? Okay. So yeah, as we said, the challenging part in this milestone is how are we going to debug cases, like you're going to run into cases, or you're saying that my code looks correct, but I'm not able to find the optimal solution, or it's failing at certain test case. And that's why we divide again the unit tests. So we start with the simple test cases, simple underscore whatever, legality or optimality. Try to test those first. Try to make sure that you are passing those first, because again, these are between intersections that are like one hop away from each other, or like 2 hops. So if they are working, then try to go to a larger test case. So find, for example, now nodes that are 2 hops away. If they are not working, then try to use the debugger and step through or put breakpoints in your code and make sure that it is doing what you expect it to do. So these test cases are for you to be able to debug your algorithm, because otherwise, when you go to the larger test cases and the more complicated ones, it's going to be very hard and very time-consuming to find where to root cause where the issue is. Okay. So once you are sure that you are able to pass all of these simple legality ones or simple optimality ones, try a slightly harder test case and try to increase the distance between the intersections you're trying to find the path from. For example, go to 2 intersections apart, and again, use the debugger if they are not working. Make sure your code is behaving exactly as you should. Okay, then you jump to all of these cases, more general cases where the intersections can be anywhere in the city. And here is going to be a little bit harder to debug, but knowing that your 2 intersection legality checks work fine, it should be easier for you. And we divide these actually test cases into 2 parts. One with term penalty 0. So the algorithms that we discussed in lecture all assume that the term penalty is equal to 0. Okay, so if you take the lectures, if you take the algorithm from the lectures as is and try to code it, it should at least pass the tests that have term penalty 0. It's up to you to include that extra term penalty. So to make it easier for you, try to make sure that you are passing the test cases that have term penalty 0, because let's say that you are able to pass those and not pass the ones with term penalty, then you know that you have a problem with your term penalty and where to look for. Yeah, go ahead.
Do the test cases or do they just run the code?
We will always call your load map first.
But the test cases themselves, like, they won't open the map right?
Oh, you mean the visualization?
Yeah.
No. When you submit the visualization is disabled. I'm going to talk about this in a second. So the visualization is disabled when you submit your code, like when you run the Excel.
We don't need to change anything in main.
You don't what?
We don't need to change anything in main.
No. So that's for the demo part when you demo to your TA. Yeah. So yeah, again, test first with term penalty 0, and then once you know that this is working fine, go ahead and test with the term penalty not equal to 0. Okay, there are also extra unit tests for val grind in order to make sure that you don't have any memory issues. So the val grind test is useful to check for memory problems. In ECE297 exercise, it's running on St. Helena as well, similar to milestone 1. You can also use ECE297 exercise 3-dash debug tester to get the val grind command if you want to test it on some larger map, or like you found an issue that it's going out of memory or something, okay? The debug check build is also important in this case. It helps you also check for memory, but it also makes sure that all of the STL containers that you're using are valid. So if you're using a vector, it makes sure it will report to you that if there is a memory, an out-of-bound access on that vector, for example, or if you're using most likely you would use a priority queue or a heap in some sort of another in this milestone. So it makes sure that this heap is still a heap. So sometimes users do, students do like some crazy things with pointers that it's not a heap anymore and it's like invalidate the data structure. So the build check, for example, makes sure that you're still using a heap, which will help you also debug problems that you're gonna run into throughout the algorithm. Okay, so that's it regarding the unit test. Now, speed tuning. So again, we test again for performance. Why? Because trying to find a path is very important in this course and in the industry, as I'm going to talk about in a second. And these usually, whenever you try to speed tune your algorithm, these are usually divided into 3 categories. One, try to change the whole algorithm. The algorithm is the most important one. If you're using the wrong algorithm, then whatever you do, you'll probably not be able to optimize it further, okay? Once you choose the right algorithm, sorry, then it's important to look at the data structures you are using. So are you using, for example, a vector to search for a node? Are you using like a set, for example? So choosing the right data structure is also important. And finally, when you are like out of choices in the first 2 categories, you look at the low-level code. Some students jump directly to this level 3. Whatever you do, you'll probably not be able to pass the test if you don't change your algorithm or don't change your data structure first. So like whenever, even in the industry, whenever we try to speed tune something, the first thing we look at, what is the algorithm being used? Can we do something better? Like in terms of asymptotic time complexity, is this better or not? Okay. Then we look at the data structure and then we try and fine tune the code. Okay. So another thing that is useful to debug is to visualize your algorithm. So if similar to what we showed you, to what I showed you in the demo for the golden solution, try to build something that helps you debug how your algorithm is progressing. Because once you go to the very large test cases, it's going to be very tedious and very hard for you to follow each and single street segment or each and single node that you are traversing in the graph. On the command line without visualizing. So if you're visualizing it, it will give you at least like, is your algorithm overall doing the right thing? So for example, in A star, is it more of an oval shape or like a circle shape, right? So we use the graphics to animate and visualize. So, but make sure that not to leave the visualization in your final submission, because now the M3 auto tester again will disable the graphics, but still it may slow you down if you keep it on in some way that we don't know about. Okay, like if it's right within the algorithm itself, we're not sure that you're using graphics or not. Sorry, go ahead, Arnaud.
So could we submit like one branch which has like graphics disabled, so it runs the code, like just the test case code, and then demo from another branch, or is it not?
What you can do is this, basically. So use a macro to define visualize. When you submit, just disable that macro to make sure that the visualization part of your code is disabled, and wrap all of your visualization code within that macro. So if it's defined, then it's gonna be compiled. If it's not defined, it's not gonna be compiled. Does that make sense?
Where do you define?
So it's like just a macro that you can define on top of in some header file of your code, or like at the top of the CPP file. Make sense or no? No? Sorry? So no, it's like, do you know how to use macros? Like, yeah, so it's just define macro, Okay?
You mean comment out the entire header?
No, not the entire header. You just comment out this line. Okay? So this is, let's say, this is the code to do the visualization, right? We are wrapping it around inside if def visualize. So if visualize is defined somehow, then the compiler will look at this and try to compile. If it's not defined, then this is not going to be compiled. And we do this by just commenting out this line. So when you submit, you just comment out this line. And when you want to demo to the TA, you just show them that I'm going to uncomment this because this is for the visualization. And it will recompile and you will enable the visualization in your code. Does that make sense? Okay. So again, we're trying to animate. This is a small code that you can take as is and try to run it. I'm not going to go in the details, but basically we're trying to animate the path that we're trying to search for while the algorithm is running, right? So we highlight the street segment, the next street segment that we're going to visit with some color. In this case, it's blue. And then we call flush drawing. Flush drawing basically tells ECE297 that we're not going to wait for a user input to redraw, just to go and redraw immediately. Okay? So this is going to redraw the next edge that you're going to visit. And then we call this delay function because without this delay function, the drawing will be very fast and your algorithm is very fast that it's going to be hard to actually see what's changing, right? So we try to delay a little bit. And this delay is, we define it to be in terms of millisecond, and it's using the chrono library with a sleep4 function. So this sleep4 function, this line, will just tell the chrono library or tell the program that don't do anything for the next duration, in this case, 10 milliseconds. Yes or no?
Do we need that, or is that just for aesthetics?
So you don't need that for the demo. This is just for you to debug. For example, you saw in the demo that I showed you how we are visualizing this. I added this delay 0.5 millisecond, for example, because otherwise it's going to be very, it's too fast to actually see, right? But again, notice that with this delay, if you submit without these macros and try to run, the autotester tries to run your code, it's going to be very slow because every iteration it's doing nothing for 10 milliseconds, right? So just make sure that if you're using graphics to debug your code, that to disable it when you submit. Okay, any questions on this? Yes?
So would this chunk of code be placed in the part of the Dijkstra's or A-star?
Yes, so inside the loop, yes.
Of like, we're going to visit these like street segments next? Or
I would put it inside the while loop, like when you pull the next node to visit, yes.
Okay.
When you so the big while loop, when you pull the next node to visit, you're checking whether you're gonna visit it or not, right, based on its best travel time right now. And if you're gonna visit it, then just draw the edge that you use to reach that node. Okay? Okay. The other thing that you can do is to use the profiler to see how long each of your functions is taking. So there is a quick start guide and also tutorial 7 talks about how to use the profiler. And you can draw these flame graphs, which is basically, which spans your whole program. And from it, you can notice that how long each of your functions are taking. So for example, in this case, in our golden solution, the turn computations are taking this much from the overall time, and then the finding connected segment info, how to like query the data structures, and finally the priority queue operations, like which is the largest amount of work that we're doing to heapify, etc. So all of this, for example, makes sense to us. So like you can do something similar in your code to make sure that your functions are running at the right time that you're expecting them to do. Okay, so there are two ways to do this. There is something called the profile build and the release build. The release build is what we usually run to your exerciser with. The profile build is a bit more detailed than the release build, and it has only one less optimization from the release build, which is called function inlining. Function inlining means that whenever you call a function, the compiler will try to place the actual code of that function inside the location that you called it, so that it makes the execution time faster. Okay, but the good thing about no function inlining is that it actually gives you all of the details of all of the functions that you're running on, So it doesn't hide any information from you. So this is very useful when you want to basically test every single function that is running at the same time that you're expecting it to do. But then once you get that idea, you run with the true picture. The true picture is with the release build. So it's less detailed, but it's the actual execution time is going to take, and it's the execution time we're going to use to test your code. Okay. Questions on this? I think that's, oh yeah. So I'll use the last 5 minutes to talk about a little bit about, so that's it regarding milestone 3 and the algorithm. I'm gonna talk about now, why do we care about finding paths so quickly, right? So we talked about one application, which is in the city map, trying to find the route between two intersections. And we know that the cities can be very big. So for example, in Tokyo, it's more than 1 million nodes. So trying to find a path quickly is better for the user. It's more usable, and it also allows us to do other kinds of algorithms like milestone 4 traveling courier, which is what we're going to talk about next lecture. But there are also other domains where we use like things like A-star and Dijkstra, and it's very important to have these algorithms that are running very quickly. So in FPGA design, so my PhD supervisor, basically his main domain is in FPGAs, and in the research group we did a lot of these, we worked on a lot of these kind of problems. So if you remember in 241 you used Quartus, which basically tries to program the FPGA. And one of the algorithms that Quartus tries to do is to route your design, okay? So in a typical FPGA like this Stratix 10 FPGA, there are usually around 43 billion transistors, okay? These constitute around 10 million logic elements, and we need to connect about 40 million signal paths in a wiring graph. And the graph size is around 300 million nodes. So notice how much bigger it is from Tokyo. Tokyo has around 1 million nodes. This has 300 million nodes. So that's how big the graph is, and that's how significant it is for you to have a very quick algorithm. And we are trying basically to find 40 million path searches in this algorithm, okay? So if you're running on an engineer server and it's not running very quickly, it's probably gonna take you years to run, right? So next time you're running Quartus and you're saying that, oh, Quartus is very slow, you should appreciate that it's actually doing a lot of work and it's actually running very fast. Because it's a typical Quartus time is around a couple of hours for a whole FPGA. So what Quartus does is actually it goes beyond A-star. So right now we taught you A-star. What Quartus does is trying to find a directed search plus some heuristics. So it doesn't care anymore about the most optimal solution. If it finds a solution that is good enough, what is good enough, that depends on the developer. So if it's good enough, it's going to take it and assumes that this is the solution it's going to take. And these are all kind of trade-offs in computer-aided designs we take so that we try to find solutions faster and try to come up with designs faster. Okay, so this is with a chip that's 43 billion transistors. Now in Cerebras, for example, the chip that we use that I showed you in the first lecture, it constitutes of 2.6 trillion transistors. And that's too many zeros. So these 2.6 trillion transistors, they constitute around over 850,000 processor cores. So in a typical server that you use, it has like 4 to 8 cores, right? This has 850,000. And we need to connect millions of data transfers through interconnect graph with millions of nodes, right? So again, we want to find shortest path in a relatively very short time. So we use in Cerebras things like the A-star. We use an algorithm called Pathfinder. It's a popular paper in FPGA design in order to be able to find the route between two nodes, any two random nodes on the chip, on this big chip. There is something called a network on chip, which is like small internet on the chip that has routers on them to route from each processor to the other, and we use those as our nodes in order to be able to find the paths quickly. I'm not gonna go over the details. I'm just trying to show you why it is important to have very fast path search